Hi everyone, this is part 1 of chapter 8. It's an introduction to acids and bases. Let's get started. Your book starts this chapter by mentioning that acids and bases are probably the most important topic that you're going to learn in chemical equilibrium. I do agree with them. I think that to have any sort of intelligible discussion about equilibrium, you're going to have to know about acids and bases. First of all, the basic thing is we got to know what an acid and a base is. So in aqueous chemistry, an acid is a substance that increases the hydronium ion concentration. A base is therefore the opposite, right? It decreases the hydronium ion concentration. And that, of course, means necessarily it increases the concentration of hydroxide. So as your H3O plus goes up, the other one goes down. As your H3O plus goes down, the OH goes up. I'm showing you there just a cool picture of what a hydronium ion might look like and the size of it. Not important, just I thought it was a cool picture. So your book uses H3O plus or H plus interchangeably, even though H3O plus is really a more accurate description of what's going on, because in water, a proton doesn't sit around by itself. It actually is an H3O plus. But, like I said, your book uses them interchangeably, so don't get confused. Now, a quick sanity check. Why is it called a proton? And I put duh there because everyone should get this, right? It's called a proton because what happens, how do you get a proton? It's because when you remove that electron, that only electron that hydrogen has, what are you left with? You're left with a proton. So that's what we call it a proton for. All right, let's do a little bit more general definition of what acid and base are. The Bronsted-Lowry definition states that an acid is a proton donor and a base is a proton acceptor. And this is a really cool definition because it actually can be extended to non-aqueous solvents. For example, you see on the bottom there, you have hydrochloric or hydrogen chloride, right? Because it's not an aqueous solution. Hydrogen chloride is considered an acid even though it's not in solution because it's able to donate a proton to ammonia gas. You notice the product there is ammonium chloride. NH3, of course, is considered a base in this reaction because it accepts a proton. But they're not in aqueous solution, but they're still considered acid and base. So that's why the Bronsted-Lowry is a really cool definition because it's a more general definition. And on the top, you obviously see the one that we would see in aqueous solution. So hydrochloric acid, I should have AQ down there, but I don't. Hydrochloric acid is considered an acid because it donates a proton to water. So water in this case is considered the base because it accepted the proton and became hydronium ion. All right, we got to learn about salts too. And just as a reminder, salts are any ionic solid, right? So the example that I gave you works for this, ammonium chloride. And formally, a salt can be thought of as the product of an acid-base reaction. You should start remembering these things from general chemistry. When an acid and a base react, stoichiometrically, they actually neutralize each other. And of course, most salts are really strong electrolytes. So for example, if I was to stick that solid, ammonium chloride, in water, back in water, it's going to completely dissociate into ammonium ions and chloride ions. All right, what about conjugate acids and bases? Well, these are acids and bases that are related by the gain or the loss of a proton. So for example, look at acetic acid on the left there, right? Acetic acid is being reacted with methylamine. Acetic acid is obviously considered an acid. Methylamine is considered the base because you notice in the product side, the acetic acid turns into acetate ion because it donated the proton, right? And methylamine, which is considered the base at the beginning of the reaction, is the one who's accepting that proton and becomes methylammonium ion. Well, if you notice, now the acetate ion can actually accept a proton and become acetic acid. So this goes back and forth, and that's why they have that little double-headed arrow there, because it's an equilibrium. These things go back and forth. But both the acetic acid and the acetate ion, as well as the methylamine and the methylammonium ion, are related because the gain or loss of one proton. So they're called conjugate pairs. They're called conjugate acid-base pairs. So acetic acid is the conjugate pair of acetate ion. Acetic acid is the acid, the acetate ion is considered a base. And the same argument goes for the methylamine and the methylammonium. We're going to start talking about equilibrium a lot, but the first thing we got to do is learn what the relationship between hydrogen ions, hydroxide ions, and pH. So water is obviously a universal solvent. It's really important to most reactions that we do, or most chemical equilibria that we're going to talk about. And the reason it's really important is because it's one of those substances that can act both as an acid and a base. It depends on what environment it's in. And remember what I said, that you rarely find H plus in water, okay? It's really either going to be a water molecule, it's like the H2O, neutral, or you're going to find a hydronium ion or an OH ion. You're not going to find single H plus ions all over the place. That doesn't happen. So as a definition, autoprotolysis is a substance that acts both as an acid and a base, and water would be one of those substances. That reaction on the top is just abbreviated. It's the same reaction. It's just abbreviated on the bottom. So you have H2O in equilibrium, right, with H plus and OH. So if we wanted to denote that, we would say that the equilibrium constant of water, K is the symbol for equilibrium, so the equilibrium constant of water is equal to 1.0 times 10 to the negative 14th. This is a constant at that particular temperature, at 25 degrees Celsius. We're going to talk a lot about equilibrium constants, but you'll see that when you write an equilibrium constant, it's going to be the products divided by the reagents. So here you have the H plus and the OH, which are the products of the reaction, but we don't have anything as the reagent, right? Even though you see that water there, we don't put that on the bottom because it's a pure liquid. And you'll understand that more as we get further and further into this chapter. So the equilibrium constant of pure water is made up of the concentration of proton ions and the concentration of hydroxide ions. And that ends up being 1.0 times 10 to the negative 14th molar at 25 degrees Celsius. And again, that is a constant. Let's do a problem now to kind of get ourselves accustomed to this equilibrium constant of water. Let's calculate the concentration of both the H plus and the OH minus in pure water at 25 degrees Celsius. Okay, so we use the definition that we just learned. The equilibrium constant of water is equal to 1.0 times 10 to the negative 14th. And that is made up of the products of that reaction. So it's H plus and OH minus. So we have to calculate the concentrations of both of these. So we're going to put both of them as X's. From here on down, it becomes a simple math problem. So you have two X's, so that's X squared, is equal to 1.0 times 10 to the negative 14th. So how do you remove that square from the X? You just take it onto the other side by making it into a square root. So you would have X is equal to the square root of 1.0 times 10 to the negative 14th, which ends up being 1.0 times 10 to the negative 7th molar. So the concentration of H plus is 1.0 times 10 to the negative 7th molar, and the concentration of OH also is 1.0 times 10 to the negative 7th molar in pure water at 25 degrees Celsius. We're going to do more problems like this in class, but you'll see this is really, really easy. What about if you wanted to find the concentration of OH when you know the concentration of the other one, of the H plus? Well, it's also a very simple math problem. Here, again, you use the constant, right? So the constant is 1.0 times 10 to the negative 14th equals to the concentration of both those things, but of both the H plus and the OH. But they gave you the H plus concentration, so it would just be 1.0 times 10 to the negative 14th is equal to 1.0 times 10 to the negative 3 times the concentration of OH. So you solve for the concentration of OH, and you see that you end up getting 1.0 times 10 to the negative 11th molar. Remember, the constant was negative 14, so if the H plus is negative 3, then the OH must be negative 11. Remember, they have to add up to negative 14. That's the constant. So you really don't even have to use your calculator for this. You can just figure it out in your head. Let's start now the conversation about pH. This is probably what a lot of you are more familiar with. The definition of pH for right now is negative log of H plus. The reason I say that is because that's not the real definition of pH. It's an approximate definition. the real definition takes into account ion concentrations and activities, but we're not going to get into that right now. So for right now, pH is equal to the negative log of H plus. Let's make sure we know how to use this equation. So if I told you that the concentration of H plus is 10 to the negative 3, I want you to tell me what the pH is. So you put 10 to the negative 3 in your calculator, press the log button, and you'll see that you should get negative 3. But you have to remember that there's a negative in front of that log in the pH equation. So that negative 3 actually becomes positive 3. If you have an H plus concentration of 10 to the negative 3, your pH is going to be 3, which means it's a really acidic solution. What about the next one, 10 to the negative 10? Well, if you follow the same logic, this one's going to be a pH of 10. Very simple. That one's a basic solution. What about the next one? If you put 3.8 times 10 to the negative 8 molar and press log, you should get negative 7.42. But remember, you have that negative, you got to remove it, so it would be a pH of 7.42. It's actually sort of neutral, this solution. So you can see here that if you change the pH by 1, it actually changes the concentration of hydrogen ions by a factor of what? By 10, right? It's a log. So by the factor of 10. Now, what if I wanted to go backwards, right? So what if I gave you, okay, the pH is 10. How do you find the H plus concentration? Well, in my calculator, I press 10 negative, right? Because it's negative 10. So 10 negative, and I press the second function, and there's a button that has 10 to the x. I press that button, 10 to the x button, and that gives me 1 times 10 to the negative 10th, which is the concentration of the protons in that solution. So here's the scale you guys probably have seen before. It's the pH scale, and most of us know that pH scale from 0 to 14. I want you to realize that those are not set limits, all right? There are things that have pHs lower than 0 and higher than 14. For example, what if I gave you a pH of negative 1? This is actually the pH of really, really concentrated acids. Like hydrochloric acid has a pH of negative 1. What is the concentration of hydronium ions in a solution that has pH of negative 1? I would put 1, second function, that button that says 10 to the x, and you'll see that it's a 10. So it's a huge amount of hydronium ions because it's a really, really, really acidic solution. All right, just as a take-home message, obviously if you're in acidic solution, the concentration of hydronium ions is going to be way greater than your concentration of hydroxide ions. And in the basic solutions, it's the opposite. The hydronium ions are going to be less than the concentration of the hydroxide ions. All right, guys, this is it for this video. I'm going to resume in the next video and start talking about the strengths of acids and bases. All right, see you later.